To this computer. All right, welcome to HMI Design. I call it the good, the bad, and the ugly because there's a lot of ugly HMI design. In this presentation, I will expose you guys to one of my hugest pet peeves about designing any kind of automation system. It's the fact that the designers usually don't understand how people work. And they're certainly not artists for the most part. Engineers in general don't tend to really do a good job of understanding people and how people work. So what we're going to be doing is we're going to be diving into good design, bad design, and we're going to talk about HMI in general. Now, when I talk about HMI, I'm talking about more than just a display. I'm talking about anything that's a human machine interface. Most people, when they think about HMI, they think about this kind of object, which is a display screen, human machine interface. I can program it. I can make pretty pictures on there. I can have push buttons on here. It's a touch screen. It's easy to install in the panel, and this is easy to work with automation. They've been around a long time. This is a more typical sized HMI. This is from Phoenix Contact, an excellent company. We don't use it because it's a pain in the butt to program, but this is a large size HMI for its time. And now it's not even a large size HMI. Now you can have HMIs that are much, much bigger than this. These tend to be small, dedicated microcomputers. And in those microcomputers, you've got dedicated memory. They tend to have interfaces to the Ethernet. Sometimes they have interfaces to Wi-Fi. Generally speaking, they have USB connectors on them, power connectors on them, so they can hook this sucker up and run it almost like a little computer. Now, in addition to HMIs that are traditional dedicated HMIs, I also include in this category SCADA systems, which is an HMI that runs on a computer screen. Supervisory control and data acquisition systems. Those essentially are HMIs, but they're not just for dedicated devices. They can be on your laptop computers. You could be sitting anywhere in the world looking at the HMI for your machine that you're monitoring real time, as long as you have good Wi-Fi. So, and we also have dedicated computers out there. And let me go out of frame here to go grab. This is a dedicated computer, industrial computer. And I've been building these. Oh, hopefully not drop this on the ground, but I've been building these. And the purpose of these is that we can have a dedicated computer that then hooks up to a SCADA system that then also I could use for programming the PLC. So I can program the PLC from the same device. This little guy right here is also from Phoenix Contact, and it's got its own power supply that I would mount separately, and I would mount a PLC right here on the top as well. So this whole thing would generally be inside of a control panel. I just happen to use this to stick the schedule up, so ignore that. You can tell I haven't used it recently if I stick schedules up to the screens of the device. All right, so that is a typical HMI as well, but it's also a computer system. So I just want to expand your mind with HMIs a little bit. So in this presentation, we're going to dive into some details on HMI. And so to do that, I'm going to, there we are, talk about content. So we're going to talk about objectives. That's this section here. We're going to talk about war stories. HMIs can kill, and I'm going to give you examples of that. HMIs, badly designed HMIs can kill. Oops. Apparently this presentation is designed to run. Slideshow, let's not. Why did it have timing set on? Okay. All right. Let's try this again. Let's share again. Oy vey. I might have to edit that out. And we're going to share the presentation. All right, here we are. Good, the bad, and the ugly. All right. So we're going to talk war stories. We're going to talk about requirements. We're going to talk about scope creep and testing plan. Requirements are the list of things that your customer, your boss is your customer in many ways, give to you as things they want the system to do. The number one way to kill a project is to keep adding things for that project to do. We call that scope, the list of things that your project does, scope. And when people add things to it, we call that scope creep. That creep kills projects. You might say, oh, they just asked for this little thing. This little thing, though, requires extra testing. It may actually cost more in terms of extra hardware, software. And if you keep adding one little thing after another, you find that in the allotted time, there's no way you complete the project. So you really have to watch out for scope creep. You have to develop a way to test it within the time frame allotted. And frankly, if you're our technician building systems in the plant, writing an HMI, or even just modifying an HMI in the plant, you need to do it relatively quickly. You can't take forever tweaking and tuning just because some supervisor, some operator tells you so. All right. So you need a testing plan that tests specifically everything that you understand. The next area I want to talk about is understanding the users. We're going to dive into that a little bit more. Who is your user? What do they need? Sometimes users think they want something that isn't really what they need. We're going to talk about templates as well. Templates is how you keep your HMIs looking good, right? We're going to talk about that. We're going to talk about navigation, menu structures in HMIs. A super simple HMI like this may not have a menu at all. It may just pop up and show you 3 buttons and 1 indicator. And that's great. But more times than not, engineers will love to give you multiple buttons, multiple indicators that are all on the same HMI. And you guys are going to have to do that in this class. You're going to have to give me menus and multiple buttons and multiple indicators. So I can create a menu structure in this HMI just like I can for any program out there. I can have menus. So we're going to talk about that menus. We're going to talk about the templates to keep you honest. We're going to talk about navigation and layers in screen design. We're also going to talk about how you present data. How do you present data that gives it the most impact, that doesn't confuse your users? So we're going to talk about that a little bit. We're going to talk about alarms. One important function of a HMI or a SCADA system is both the history and the alarms. A lot of systems have reasons why they might start being a major problem. So you want to have an alarm that'll go off that'll bring the right attention over to the right thing that needs to be fixed and have the operator deal with it. If you have alarms that don't bring your attention to the right thing, or maybe too many alarms that go off, we're going to talk about that, you've got an issue. We also want to talk about alarm reactions and historical data. Anytime you've got trending data in an automated system, that might be very interesting for troubleshooting. So we're going to talk about that. And last but not least, we're going to touch a little on methodology for testing. So our objectives go back to the original course objectives. And so our main objective here, there's 5 of them, are to main objectives. Talk about HMI design, good design. And this is a lot of my opinion based on my experience. I started doing HMI design in the early 90s. So how many years is that?
A decent amount.
What's that?
A decent amount.
A decent amount of years. And even before that, I was doing programs on PCs. I was writing programs for PCs back in the early 80s. In fact, I think I started writing some PC programs in the late 70s. So there you go. So we're going to talk about what good design is, and it's mostly my opinion, but I think it's a pretty good opinion. We're going to talk about operator interaction. We're going to talk about screen design, menu design, and conveying knowledge. The objective I'm going to have you guys is the ability to convey knowledge. That's different than information, knowledge in a limited space. This is kind of an art. There's no science to it that I know about. I mean, there's lots of science that could go into it, but the art of giving you a really good bit of information on a small screen, giving you just the information you need when you need it as an operator, that's absolutely critical. And so figuring out how to do that is good design. Now, you guys will be in the position in most plants you work in today of not having any control over the HMIs around you. But you will have this remarkable position of being able to criticize the snot out of them, take notes on all the ways you can improve the HMIs around you. Maybe someday you'll get to reprogram them. So I want to talk about a little war stories here. If we talk about HMIs, bad HMIs can cost a lot of money and in some cases cost lives. People hitting the wrong button is something that's happened ever since buttons were created. And in some cases, the wrong button meant they got blowed up. They died. All right. In some cases, they just killed somebody else. In the case of a factory I was in, we had an operator who walked off, left a programmer working in the facility that he was in, and that programmer figured that the plant was empty, he could run through some simulations. So he started running through simulations, but he did not observe his HMI properly and didn't realize his simulations were live in the plant. Unbeknownst to him, there was some technician down in the plant working on a caustic line, replacing a valve. The technician was like, I'm alone in the plant. Nothing's going to happen. He didn't bother locking out and tagging out the caustic line to where he was removing a valve. So the two people came together, bad lockout, tag out, bad HMI design. Long story short, the technician got a face full of caustic, 6-inch pipe, high pressure, killed him pretty rapidly. And it wasn't a good way to die. And so that was a company I actually worked for. I wasn't there at the time, but that was a company that I actually worked for that were partly responsible for letting that happen. So that's my war story. Another example war story is 3 Mile Island. 3 Mile Island is a classic case of too many alarms going off. In those days, their HMIs were push buttons and indicator lights. But just like screens today, those push buttons and indicator lights could be bad design. I could have too many push buttons and indicator lights. So let's go look at that slide. This slide. All right. So this is what a control panel looked like at 3 Mile Island. Isn't that crazy? Now, if you started having flashing lights go off on this control panel, would you know what to do when that flashing light went off? Well, one would assume you'd walk over to that flashing light, read the legend on the indicator, and then you would go take some action, maybe pull out a big book, search up what you have to do, and you go fix it. Yeah, that's okay if you have one indicator light going off. But at 3 Mile Island, when they had their reactor meltdown, what happened was we had one pump failure lead to an overheat, lead to another failure, to an overpressure failure. They had a cascading set of failures with one source cause. But when that operator rolled into the control room, looked up at his control board, he saw nothing but flashing lights and beeps and buzzes, and I think a half a dozen different alarms were showing by the time he rolled in there. How is he supposed to address that situation? Now, if he had understood what the root cause was, he would probably have had 2 to 3 hours to fix the problem. The operator did not figure out the root cause, and then the plant melted down. I guess this was the 70s. So this is an example of bad HMI design. Nobody died, I don't think, though we did irradiate quite a bit of land, had a little bit of release, scared everybody around here quite a bit, shut down Three Mile Island for a long time. Of course, now it's being opened up so we can have some AI juice. Woohoo! But yeah, so Three Mile Island is a classic example of bad HMI design. And they're not alone. They are definitely not alone. Um, this is an HMI design that I was involved with, I don't know, 20 years ago or so. And as we look at this design, first of all, it's kind of cool. You see a pretty picture of tanks with cutaways and smokestacks and pipes and lots of little indicators, right? It's pretty. But what happens if something goes wrong? This whole thing, it's got tiny, tiny little indicators. So I got to get really close to the screens. It's got a lot of data all over it. If I have an alarm situation, can I tell what the root cause is? No. It's got a lot on the screen. It's got too much on the screen. It's got too much crowded information. It doesn't have any logical way of tracing root causes. It's got lots of pretty pictures. And you know what? We sold it to the company that bought this because it was cool and pretty pictures. So as engineers, we're like, yes, we have a little picture of the smokestack. It's 3D. It's got shading and coloring. Woohoo! Is that helping the customer in the end, though, or helping the operator in the end? No, not even a little. So, so HMI design back in this day was was selling because of pretty pictures, but operators were paying the price. Operators hated these screens. The first time they looked at it, they're like, that's cool. The first time they ran it for a while, they're like, all right, how do I go look at this data? All right, you page down over here. How do I look at this data? You page down over here. So you had many, many long, painful discussions with operators over screens like this. And I have to admit, when I first started programming HMIs, I built pretty screens just like this. This is where I started too. And that's what we all believe. We believe pretty screens. Let me go back up to previous slide. So I've given you guys examples of bad HMI, and I've also given you a link here. So I urge you to go out to that link. I think it's still active. Let's go check it real quick. Let's check the link real quick and make sure it's still active. Does not look like the link I thought it was. But maybe it is. It looks like they've updated it. But they took away the lovely presentation that we used to be there. Okay, so I'll update this link in I'll update this link and put it out again in PowerPoint, so we'll have a new link. So let's go on. So requirements. Requirements are a way for me to document exactly what the system's supposed to do. If I have bad requirements, I will have a bad system. So what are requirements for an HMI? And so I don't really go into that in this presentation. So let's talk about what a requirement is. First of all, a requirement must be very specifically what data to display. And this includes I/O. So you always want an I/O count and any other data you want to display. All right. You always have to have in your requirement who your audience is. Audience. My spell check is not working very well. All right. You got to have your audience defined. Another requirement would be what data do you want to have input on? All right. Now that's just big lists of inputs and outputs, essentially. Third, fourth, not necessarily in the right order here, but fourth, I'm saying we've got to have an idea of the connectedness between the different objects. So we have to have grouping. We have to have grouping of your inputs and outputs. Let me give you an example. Let's say you have an operator workstation you're creating for a single boiler, right? So this is pretty easy. So you might have your primary screen for controlling your boiler pressure, which would just show you your boiler pressure. It might show you whether you're getting power from your power plant. It might show you the outputs that are turned on, the valves that are being turned on to use that boiler pressure. And so just basically a simple overview of what that boiler is doing. All right. And then you might have a subscreen. And so everything associated with running that basic boiler, turning it on and off, and viewing its operation is on one screen. So you have a data display, temperature, and whether it's running or not, data input, the on switch or the off switch, and that sort of thing. So that will be a grouping of data that you could put onto one screen for the boiler. Now you might split it into two screens depending on how big your screens are, but theoretically you could put it on one screen. So you got to have those grouped by screen or grouped by groupings of screens. And to understand how you want to group these, you have to talk to your audience, and I'm going to talk about that more later. Different operators often have a different way of viewing stuff than the engineers do. The engineers, the scientists, the managers group things in their head one way, but from an operator perspective, it might be grouped completely differently because the operator knows that, hey, when this machine is on, it causes a big draw to the boiler, and I got to go back to the boiler room and crack open a cooling valve. Not that that's a realistic example, but that's the kind of thing that an operator may think of. They've got to go do this when this happens. So having an overview screen here showing with just an indicator on the left what machines are running, consuming the boiler pressure, that might be useful little bit of data for that operator. So you want to have a grouping of understanding in your setup. The third are conditions for operation. You have to lay out all the different conditions you might be. Boiler, cool, shut down. Boiler startup sequence, second condition. Boiler running sequence, third condition. Boiler discharge, like you have an overheat, you got an overpressure, you have to have a discharge. Boiler shutdown. You want to have a whole shutdown process that turns off the right valves in the right sequence. So you have a series of different kind of conditions that boiler is in. You have to document each one of them, and you need to document the state of your I/O in each one of those conditions. The reason for documenting all these conditions is as you design these screens, you want to make sure that you're clear that under each one of these conditions, you could have a test. And we're going to talk about testing in a minute. But you have to be able to test this I/O, these I/O in real world conditions in real world scenarios. So this all goes back to your testing. You write a requirement and then you put a test out that tests that requirement. You should always have for every requirement at least one test. We also want to make sure there's no under the cover expectation here. All right. You've got to make sure that they don't expect something they're not going to get. And this is true whether you're a third-party vendor or you work for the guy. You really got to make sure they don't have expectations this thing's going to have, be a rocket they could take to the moon, when in reality, all they are is getting a step stool. That you really have to be clear on that. And then there's personal reasons for that as well as business reasons for that, because you can waste a lot of money shooting for the moon. So documenting any expectations by saying very specifically what's in scope and what's out of scope. All right, what areas of function are in scope and what areas of function are out of scope? You really have to be very clear in that. All right, scope creep can kill. So like I mentioned earlier, you don't want to have a case where they keep adding requirements on you. And the only way to do that is you document your requirements, you get your boss to sign off, and then you keep that printed piece of paper with you for the entire project. And as soon as somebody asks you for a little bit more, you go pull it out, you go through it. All right, we might be able to add it, but we need to add more time to the project, and we need to maybe add more money to the project. Let's go talk to the boss. And inevitably, the guy will be like, oh, never mind. 90% of the time, it'll be a never mind. Now, once in a while, you'll have forgotten something important, and your op will be like, if you don't give me this, it can't possibly work right. You got to listen to those because operators know a lot more than you guys do if you're not on the floor with them. Sometimes they do make up stuff, don't get me wrong, but in general, they know more than you know. So let's talk about operators. Operators come in all flavors. They are as diverse as any group of people ever are diverse. They're diverse in their backgrounds, and they're diverse in their understandings of the universe. They're diverse in their understandings of even how the process works. You might have two operators that have been trained together, and one of them thinks the process works this way, and another one thinks the process works that way. So you've got to develop a strategy of working with your operators. And that strategy is often making sure that you clearly set up roles and set up education around this process. So what I like to do is usually define clear roles, like, one person's an operator, one person's a maintenance supervisor, or overall plant supervisor. Each one of them is going to get a specific role. Each one of them is going to give you requirements and help you review. And when you finish developing your requirements, you're going to have each one of them with expectations about where they have responsibility to give you feedback. If you let the different operators each get their own individual feedback, inevitably you're going to create a battle because operator A won't agree on what operator B wants. The supervisor won't agree what the plant manager wants. So you have to segregate the work out so that each section of what you're doing then will have an operator or operators, a supervisor, plant manager, be the one responsible for defining the requirements and then agreeing on that's the correct result. For example, you might set up so your operators can look at the screen for turning on and off the boiler. Yay, that's good. Let them be responsible for that. Then your supervisor has responsibility of looking at the historical data, reviewing the historical data, make sure the boiler is running, when it's running, seeing that history chart scroll out, showing you the temperature over time. That might be what you assign to the supervisor. Your plant manager then is set up to look at the safety screens, right? Or maybe your safety supervisor. But your safety screens now, the screens that show you all your major problems, areas of concern, high temperature, things like that. So you divert your group, make sure you gather their input, and then each assign them their own specific requirements for testing. You also need to set up ergonomic standards for the entire project. Ergonomics means physically how hard is it for you to do it. Also mentally, how hard is it for you to interact with it, to do it and to interact with it. For instance, physical ergonomics might be your seating position while you're looking at an operator screen. You want to have a seating position that matches your plant ergonomic standards. Generally speaking, that means you're not going to be sitting on a stool. You're going to be seated in a chair with an adjustable height to it so that they can get a comfortable seating position looking at their station data comfortably. Or standing is also possible if it's short-term duration, if they really need to stare at it for any length of time. You want to make sure their push buttons are easily reachable without having to extend out. And you're going to make sure they're not doing anything requiring complicated finger movement and grabbing that could cause carpal tunnel syndrome, especially if it's repetitive movement. All right, so you want to really step through all the basics ergonomics, and this isn't something that I need to tell you because most plants are going to have standards for this. This is something that you're just going to have to make sure your HMI complies with. Another few aspects of HMI are the mental aspects. When I not really mental, we'll call it visual and mental. Anyway, some people are colorblind. And often red-green is colorblind. So if you make something red and you flash it green, a person with colorblind red-green will never know it flashed green. They will be completely unaware of that. So colorblind is something else you need to allow for. So you have to think about colorblindness. I think somebody told me 10% of the population is colorblind, red-green colorblind, which is way more than I thought.
It's to varying degrees.
Yeah. So colorblind is a really important aspect of ergonomics. Button size. Do you have big fumbly fingers like me? Do you have little nimble fingers? All this. You want to be able to press buttons easily. You want to have some sort of haptic feedback in some scenarios, or some sort of feedback that the button is pressed. You want to have layout such that it's easy to access and see and make those interactions with the screen, so you don't have to slide your finger in at the right angle to get something to actuate. You want to do simple mechanical screen size, color, and access orientation. And obviously minimize for repetitive interaction, because through repetitive interaction, we create that strain, that eye strain, carpal tunnel problems, all those sorts of things that really screw up operators, make them unhappy. And this is just sort of a very short list of the things that you may want to consider about operators. There's whole books written about operator interfaces. In fact, I have one of them over there. Two of them, as a matter of fact. So operator interfaces are a whole separate world of experience and design. So we're just going to go with common sense for most of that for our smaller HMI requirements. So because our users are so diverse, we always develop, after we set our requirements and our testing requirements, we set up training. You got to get all of these users on the same track. So you've got to set up a training plan for different levels of users, depending on their interaction. And you have to build the overall user expectations into the training plan so that everybody is now starting to get trained on the same set of expectations for the HMI. Why is this true? Because you're still going to have one or two users who told you some crazy stuff, and they're going to insist that it work like they want it to work. But you got to bring them around and train them up, at least train them on how it's going to work. All right, so let's go back into the actual HMI design. HMI design. Are you guys ready for that? The actual HMI design. Let's go to this screen right here. Templates. HMI design is always a screen or a series of screens. And if you move from screen to screen to screen, and things move around, and colors change, and the positionings change, and the fonts change, and the orientation changes, then you've got a problem. You've got a real confusion for your users. And your operators will be a little bit annoyed. Now, they could get used to anything, but you don't want them to have to be used to everything. So I always suggest that the first thing you do, now this is just a suggestion, this is my design, is you develop a training template. In that template, you say all future screens will follow this template. And I always like to borrow. Find some HMI that they all agree they love, and look at the template in that HMI at that plant and say, all right, they all love this stuff. Can I use that sort of general layout and template for my HMI because I don't want to reinvent the wheel. And most importantly, I don't want to have to retrain their eyes to go look new places for things. So I'm going to steal. I'm going to steal every time from an existing template, either one that I've already made myself from a previous plant, if they don't have a good example, or somewhere on their plant if they've got a good example. So a template is nothing more than saying, all right, on a screen, we're going to start off with a background color. What's a background color that's good for your users? So we're going to have background. All right. All right. And the background is the beginning of everything. Some people love a black background. Some people like a light background. It depends very much on the lighting in the plant and the use of that system in the plant. But you start off with a background. Then you talk about a color scheme that's making sense. You don't want a jumble of bright colors. You want a color scheme that meets that plant's general requirements for aesthetic. Because the color scheme is really not that important. Really, in the end, it's not. So you ask your plant manager to give you a good color scheme, and it's good enough. But you got to document the color scheme, so that way you don't have a jumble of colors. So for the color scheme, you're going to talk about what buttons. You're going to have button colors. You're going to have border colors. All right. You're going to have menu indication colors, like in the menu. If it's a menu item, what color is it? You got menu, right? You're going to have outlines. You're going to have basically every sort of generic thing on the HMI. You're going to have a color scheme for it. Generally speaking, simple is best. Simple black, white, maybe a nice neutral color in the background. There's a whole color science out there. If you see red, it makes you angry. If you see blue, it makes you, calm. I don't know if I believe in that in the HMI world, but there's a whole color science out there, psychology wise. So you got to come up with your colors. Third is you got to come with fonts. And you're going to limit yourself on maybe 2 sizes, maybe 3 sizes of fonts. So you're going to stick to a common font and you won't have more than 2 to 3 sizes. You're going to also stick to a navigation area. Generally speaking, I like the bottom of the screen for navigation. When I used to build HMIs, I would have my navigation buttons down here. So if I click on this button, it might go to my main menu. If I click on this button, it might go to my first boiler. This button, second boiler. This button goes to my history, and this button goes to my alarm history. This would be the temperature history and alarm history. So I would set up a standard bottom-based navigation area. Now, this is not the standard now. Today, 30 years later, we're all trained to see navigation on the top bar as some sort of Microsoft-looking sort of file tab. So we're trained to put navigation on the top. I liked it on the bottom because I wanted people to look at the top of the screen for the most important information. Like the very top of the screen, I like to have alarm information or critical data for the machine operating. But now we're all trained to put the menus on the top, so we'll put the alarm and critical data somewhere else. All right. We also want very consistent screens from screen to screen in HMI. And if you already have 24 HMIs in your factory, one job that some people like to do is they sort of make all the HMIs generally the same. It reduces your cost for training. It reduces the cost of errors. If you have one HMI that's different and a button isn't where all the other HMIs have that button, you may hit that wrong button. You may hurt somebody. So you really, HMI consistency can be a real big deal. All right. Next, I say document your navigation map. Your navigation map tells you how you get from screen to screen to screen. Usually what I like to do is I like to set up a simple flow chart kind of a scenario. In a flow chart type scenario, I might have a main menu at the top. And in that main section, I'll have the ability to go down to my other screens and return back to the main menu. Documenting this is very important. Some users be like, dude, if I'm looking at boiler 1, sometimes I need to pop right over and look at boiler 2. So you might want to add a navigation ability to pop back and forth between boiler 1 and boiler 2. All right. At any time, I might want to go look at my history. So boiler 1 and boiler 2 both need to have the ability to go look at history. So you need to document how it's going to navigate. If you have too many navigation paths to get to the same point, then you're creating too much of a problem yourself. Also, if you have too many levels of navigation, you're going to make it hard for your users. They got to page down through many levels and page back. So my recommendation is KISS. Keep it simple, stupid. Document it, minimize the multipass when you can. Obviously, some users love it, but it creates a lot of confusion. And I like pop-ups. You can do a pop-up with many user interfaces. Instead of moving to a whole different screen, you can pop up some data on that screen if you want to drill down. Like you see the boiler is operating, but if you want to know the boiler temperature, you could pop on it, pops up the boiler temperature, then pop it away again, If that particular boiler temperature isn't critical information. If it's critical, it should be on the main screen. You also should be aware of loops so that you're looping through a series of different screens just because it tends to confuse users. And I guess that's all I have to say about menus. So you're going to document your menus. Let's talk about graphics. On your typical screen, you're going to have graphics. You have to have graphics. In my world, back when I first started doing this, we had graphics galore. We had, boy, that was the time of the 8088 and the 8286 and the 386 microprocessors, and we just had Windows. Windows was just first released back in those days. And when the Windows released, everybody wanted graphics. Everybody wanted fancy Windows graphics. So we had fancy window graphics SCADA screens. And there are fancy detailed graphics, like I showed you earlier, of towers and tanks and animated fans and animated mixers. And I'd have a pop-up of some generic supervisor giving me information about something. So I'd see those face and he'd be talking to me. Now, this is back in the 80s and 90s, so it was pixelated and terrible graphics, but we love that crap. So designing for pretty is often failing users. Loving that crap does not make for good design. So I say simple is better. Even though you can put fancy graphics in there, you should not, unless there's a good reason. For instance, if you have 3 boilers and the difference between the boiler's appearance is such that by just looking at the outline of that boiler, you know exactly which boiler you're on in the plant. In that case, maybe you use a picture of that boiler as your graphic to go drill down into that boiler. There are cases where that picture is worth 1,000 words and will tell you information that's quick, good for quick decision making. So yes, there are some cases graphics are valuable, but for the most part, I say keep it simple. Don't put graphics in it. You also have to decide where you're going to put data. And I've got a little link out there to this section in D2L where I've got a document, a really good article about how to design screens. So it draws the users to the important thing based on the size, shape, color, and so forth. So you should design this so that your important data draws the attention. All right. So you know exactly what to expect. So on your main screen, you would have your critical data. You can drill down and look at your less critical data on additional screens. And so I make a few little kind of comments about that in this. Um, and I say in here, I call it discussion of the vehicle dashboard. If you're driving a car, and car designers spend a lot of time on their dashboards, if you're driving a car, your most critical information is positioned in front of you in a way that really helps you drive properly without having to spend a lot of time staring at that console. All right. In some cases, they even give you a heads up display. So it's actually even on the little windshield. So you can actually see a little number like your speed right on your windshield or what direction you're traveling and so forth. You got heads up displays. But for the most part, even down in the dashboard console itself, you're going to see all your critical data right in front of you. Your speed, your RPMs of your engine, if you're shifting yourself, you'll see indicator lights indicating you got problems. So if you have an engine problem, you have a check engine light pop up. So all that stuff is designed right in front of you. So I want you to design your HMIs as if you're designing a dashboard. All the most important data popped up right there. Quick glance gives you the information, so you can glance back up and do the most important part for you as you drive, which is to keep your eyes on the road. All right, so discussion of the cooking pot. I almost forgot why I wrote that. It might come back to me. The cooking pot. Huh. All right, I'll have to come back to that. I'm not sure what I meant by that. I have to go look through my notes, I think. I'll probably come back to it later. So let's talk about alarms next. Anytime you have any kind of HMI, generally speaking, you're going to have an alarm as well. In some cases, the alarms are going to be audible. Some cases, they're going to be light stacks like this. These are pretty obvious alarms. If you see the red light go on, you know you've got a problem. If you see an orange light go on, you know you could have a problem coming real soon. Green lights, everything is good. This is the best kind of alarm as far as I'm concerned. It's usually not audible. It's usually highly visible. And it's the simplest alarm in the world. Come pay attention to me because my light stack is right above a machine that's got an issue. You got to take care of that issue right now. Right. And that's the only time you should use a light stack is when a machine has an issue that you got to take care of right now. Or in the case of robots, work cells, I've shut down that robot work cell because I got a problem. Take care of me right now. So this is a classic alarm. The same should be true for your HMIs. You don't want a lot of flashing, buzzing, beeps and dots, and so forth. You need to design your alarms based on root cause. In other words, you can't just have an alarm for every overheat or every under pressure. You've got to think about the reasons for those alarms and build a little table deciding how those reasons can be oriented to root cause, and then allow your alarm system to give you that root cause as plausible. All right, this is problem, this is problem, this problem, possible root cause, this. All right, it shouldn't be very difficult to figure out for most systems. We're not dealing with 3 Mile Island at most plants here. So always come up with a simple chart of root cause for possible alarms in your facility and put that on your HMI. So we don't want bells, buzzers, and sirens in general. We always want an alarm history. Sometimes alarms appear and disappear. So we always want to be able to track back when they occurred and why. And we can also look at data history to see that data, certain things were happening on or off, or high temperatures or high pressures were occurring when we got those alarms. There's also the concept of an alarm silence. Many people here are aware of how alarm silence works. If you are so tired in the morning that you feel like you have to roll over and hit that silence button, there is a good chance you may miss work that day. Because a lot of people, none of you guys I'm sure are like this, but a lot of people will miss that alarm and go back to sleep and then not get up again. So alarm silence can actually have a negative influence. So we want to be careful allowing it. We generally do allow it. We generally don't want an audible alarm or a flashing alarm to keep annoying operators because they'll find creative ways to cut them off, i.e., look at that wire. Now you've cut off the alarm. So you don't want that to occur at all. You have to create an alarm silence that's common sense, and you also have to make sure you don't lose track of alarms and that they continue to raise attention to areas that might be causing a problem. In some cases, you might find out the alarm that you're raising isn't real, and maybe you should take it out of the system. Historical data is another area of importance, and we use it for presentation information. We use it for real time. If I'm tracking trying to figure out is my temperature trending up or down, just looking at the temperature alone isn't going to help me. If I flip over to my trend for my temperature, I can see it tracking up or down. So that's useful real time. And it's also useful for analyzing problems. I mentioned most of that. Last but not least, I want to talk about testing methodology. I talked about it at the beginning. We're going to talk about it at the end. Anything you build has to be fully tested. Any change you make, you may not only have to test for the area you specifically made that change, but you might find that you have to go do some regression testing and go back and retest some of the old areas again. So you've got to test your HMI. You got to test it with operators who are going to make traditional operator mistakes. There's no such thing as a dummy-proof system. So you got to test it. I say testing with the innocent, right? Test it with the operators. Test it with the people who didn't design the HMI, that are your traditional people who don't know what you're doing and therefore may just stumble into the problems that you didn't see because you're too close to the problem. We also have to do integration testing, which is testing my HMI, not just with the PLC it's running one particular machine, but if that PLC is hooked up to other PLCs and other machines, make sure that all of them work together, because sometimes a single HMI could create a problem down the line. So you want to test it. Integration. Integration means a lot of pieces and parts together. And last but not least, I'm going to say user sign-off. In your testing, anytime you make a change to an HMI, get your users to sign off. Once they finish their testing, you sign it off, you walk away. There's a couple reasons for this. One of them is simple CYA, right? If you have gotten user sign off and then the user blows something up, the user can't say, I didn't agree on that. At least he agreed on it, right? So it's a little bit of CYA. The other part is building ownership. If that user builds ownership in the system he signed up on, he's going to support it, he's going to encourage the use of it, and he's going to make sure it goes seamlessly into the production line. All right, that's all I got for today on this topic. So let's